Okay, any questions? No questions from EPEK? Sweet. We can just move on to energy notes. Okay, conservation of energy. So I already stated this, that energy cannot be created nor destroyed. It can only be transformed from one type into another. But let's talk about like in terms of types of energy. So mechanical energy, mechanical means like movement or yeah, pretty much movement. That's what it applies to. So potential and kinetic energy will cause changes in position or something like that. So those are that's mechanical energy, and these are easily transformed from one type into another. Okay, if you lift something up and then let it go, you're giving it EP, and then when you let it go, that EP becomes EK. So it's very easy to track where the energies are going. Non-mechanical energy is like energies that don't cause those motions. So this is like solar energy, thermal energy, all that type of stuff. And so thermal energy is energy that dissipates or moves into its surroundings. So when you create heat by sliding something along a table, the heat that you're creating is going into the object and the air around it. So it's not conserved really. It kind of dissipates. So there's kind of two ways we're going to do this. We're going to do conservation of mechanical energy, where we just ignore heat and say like this is frictionless. These are frictionless environments. And then we're going to throw in friction and do it again with thermal. Okay, and decide, okay, where is that heat going, how much heat is going, and all that stuff. So first off, let's look at just some examples. So a person lifts a 10 kilogram weight 1.8 meters off the ground. How much work was done on the weight? So how much energy did the weight gain? So in this case, this is just a work question where something's being lifted. So the weight is originally on the ground and then it's being lifted up there. So its energy at the ground is 0. And then at the top, it has EP. So the work that's done is your final EP minus initial 0. So EP, W equals EP. So W equals MGH. So this is just 10 times 9.8 times 1.8. Okay, nice and easy one for us. So that is 176.4 joules. Okay, that's how much energy that the object gains. That's how much energy the thing that lifts the object loses. So the person is lifting the weight. So the person loses 176.4 joules. The weight gains 176.4 joules. If the person dropped the weight, how much kinetic energy would it have when it hits the ground? Okay, so now we're saying, so this is part A. Part B, we're saying, okay, now the object is right here. It has its EP. If we were to drop it, so we just let go, what is the energy at the bottom now? Okay, it was 0. But now, so again, the two questions we're asking, is it moving or is it above the ground? Okay, at the ground, it's not above the ground, but it is moving. So it gains EK by being dropped. And law of conservation of energy says that it can't be destroyed. It can only be transformed from one type to another. So the EP here becomes the EK at the bottom. So this is your initial, this is your final. So EPI becomes EKF. Okay, it's a transformation of energy. And so this is just the EK at the bottom is 176.4 joules. Okay. I'm going to add a part C, and that is how fast is it going? Fast is it moving? Okay, so at the ground, and and you have to, it's the moment before it hits the ground. Okay, it's not when it hits the ground and stops. It's right before it hits the ground. That's what we're trying to find. So if this is this is part C. If that's its kinetic energy, then, and EK is 1/2 mv squared, then 176.4 equals 1/2 times 10 times v squared. Okay, and so we'll take that 176.4 times by 2, divide by 10, square root it, and you get v is equal to, and I'm asking how fast, so we don't have to do vector, we can just use speed. So that's 5.9 meters per second. Okay, if it was a vector, if I asked for the velocity at the ground, you would have to give me negative or positive. And because it's moving down, you would give me negative. Okay. There's a couple things that I want to look at here. The amount of energy an object has will be constant at different time intervals as long as no external work is done on the object. So if there were, let's say, friction, okay, friction would be an external work being done on the object. Then it would change the change the amount of energy at each step. Okay, so there's no external forces, so the energy is constant at every point. The weight has a specific amount of potential energy at the top, which it got from the external force lifting it, and had the same amount of energy as the floor. We just found that. If there was air resistance slowing the weight down as it fell, the air resistance would be external force, which would take energy away from the weight in the form of heat. Okay, so that's kind of along with the first point. Now, further to the first point, if I were to ask you, I'll get rid of that. There we go. If I were to ask you what type of energy the object has right here, okay, in the middle, and it's falling down, okay, we would go through our process again. Is it above the ground? Yes, it is. So it has EP. Is it moving? Well, yes, it is. So therefore it has EK. Okay, so let's call this A, B, C. The energy at A is equal to the energy at B, which is equal to the energy at C. Okay, because there's no external force. And so the amount of energy will be constant at different time intervals. Okay, A, B, and C are different time intervals of the same object. And so if I wanted to look at B, I could say the EPI at A is equal to the EP at B plus the EK at B. Okay, so there, it's all equal. It's not just one or the other. It's not EP is equal to EK. It's the state of energy at one point is equal to the state of energy at another point. Oh, I hope that makes sense. Okay, let's keep going. Oh, I don't know if I can do this. Okay, I think maybe you can click on this website. I don't think it's going to work. It's not even going to show because I'm not sharing my whole screen. It shows you what happens as a roller coaster moves from one point to another. Okay, so like as an explanation, the roller coaster at the top at point A will have EP. And then as it rolls down the hill, the EP will go down, but the EK will go up. And then at this point, at the bottom, the EK will be maximized to the point where it's equal to the original EP. And the EP will be 0 at this point because it's at the ground. Okay. And so you start with EP at A. At the bottom, it's EK. At B, this would be EP plus EK. Okay, because it's not quite at the point of A, so it has less EP. And so the amount of energy that it's less becomes EK. And then at this point, again, this is going to be EP plus EK as well. Okay, and this one as well, EP plus EK. So it's just this transformation. So it's not like energy is disappearing, it just becomes a different type. Okay, so if the speed of the 850 kilogram roller coaster is negligible at the top of the first hill, how fast is it moving at point B and C? So The reason why we're saying it's negligible is it's not zero. It just, well, let me show you. Let's find the EP at A first. EPA is going to be MGH, so 850 times 9.8 times 140. So that's going to be 850 times 8 times 140. That is 1,166,200 joules. Okay. If there were a speed, it would be super small. So let's say 1 meter per second. Okay. It's not even that. Oh, it's pretty slow, but 1 meter per second. Okay. So it'd be 0.5 times 850 times 1. That's 425 joules. Okay. So even if it was moving, it's so small compared to the potential energy that we just call it negligible. Okay, so it's not going to change the amount of energy that is at the start. So it doesn't really matter. Okay, so we have the energy at point A. How fast is it moving at point B? So we need to find the energy at B. So first off, EA equals EB. Okay, the energy at any point, any time interval is going to be equal. So we're going to say, and I'm going to change this a little bit. I'm not actually going to use the 1.16 million. I'm going to say MGH at A is going to equal MGH plus 1/2 MV squared at B. Okay, because B has potential energy and kinetic energy. Now, these are not the same H's. Okay, this is the H at A, this is the H at B. Okay, the reason I'm doing this and not using the number I just found is because you'll notice how each term has an M. M, M, M. Okay, so if you ever get into a career of physics and you're designing a roller coaster and somebody says, oh, what happens if we have a full roller coaster cart compared to an empty cart? You're going to say it doesn't matter because we can cross out mass. Okay, assuming that you're working in a frictionless environment, which doesn't exist, so you're going to have to put in M anyways. So regardless of the point. Okay, so now we can just say 9.8 times 140 equals 9.8 times 95 plus 1/2 V squared. Okay, so it just makes it easier. It makes it less or smaller numbers to work with, so it's a little bit better to work with. So 9.8 times 140, and then I'm going to subtract 9.8 times 95 right away because I'm subtracting that EP from the other side. So this is going to be 441 equals 1/2 V squared, so times by 2, and then square root it. And you get V is equal to 29.7 meters per second. Okay, that's pretty fast. Okay, awesome. The next part, just trying to make sure this makes sense. Yeah, that makes sense. So the next part, we need to find the velocity at C. How fast is it moving at C? I'm not going to use the energy at B. I'm going to use the energy at A again. Okay, because it doesn't matter. It's the same everywhere. So I'm just going to go EA equals EC and go and do it again. MGH equals MGH plus 1/2 MV squared. Cancel, cancel, cancel. And so then this is going to be 9.8 times 140. Again, that's our starting point. And then I'm going to subtract the other one right away. So minus 9.8 times 80 equals 1/2 V squared. This time I'm showing it instead of that. So we can go 140 minus 80 times 9.8. So that's 588 equals 1/2 V squared times 2 square root. This is even faster. V equals 34.3 meters per second. And that's it. That's the answer. So the whole point of this is that the energy at one point is going to be equal to the energy at a different point. And that's it. That's conservation of energy. Okay. You know what? Maybe I don't want to add heat. Let's not add heat. Okay, that would be better if we were doing like efficiency and stuff like that. Let's just skip that part. The important part is that we understand conservation of energy. Okay. Now, if there were heat, if there were, let's say there were friction between point A and B. Okay. So conservation of energy still exists. So the energy at point A will still equal the energy at point B. Okay. So the EP at A will still equal the EP plus EK at, the EP at A will equal the EP plus EK at B, but you will lose heat during the process. And so we add it as a product, okay, kind of like chemistry, exothermic, I guess. So energy that's lost is part of the final state of energy, okay? And so that's the big difference. And the reason why you can't cancel M is because EH doesn't have an M in it. So that's the biggest difference, that you have heat being created, and that's it. Any questions about conservation of energy? No. Okay, so this gives you slightly over an hour, excuse me, before we meet again to talk about momentum. So go ahead and get working, and we will meet up again at, oh, give me 1 second. I need to do attendance. I'm gonna stop recording because we're done the lesson. More people are here, so.